All right, so here we are, week 23, doing some physics, and we get to talk about sound waves this week. Here's a little overview of the topics we're going to cover. Some of this is review. I just want to make sure we understand this because we talked about simple harmonic motion and we talked about waves, and we're going to talk about waves on a string and sound waves in air, and the two are incredibly similar. So go through some examples of reflection, superposition, constructive and destructive interference and standing waves, and then talk about sound waves. And yeah, like that. So, first of all, reflection at boundaries. So, we saw this type of situation where a wave pulse comes in. Looks like this end is fixed, and let's see, it is reflected, so the wave that bounces back will be is the reflected wave, and it is inverted. So this is upright, this is inverted. Alright, and then if the end is fixed, the pulse comes in like this and is reflected in the upright position. Alright, so waves bouncing back and forth. And in this type of situation, we have a wave in a light string, and what it's doing is it's hitting a heavy section of rope or string or whatever. And what happens is part of the wave is reflected and part of it is transmitted. So we're going to see this in sound waves where we have air columns, and the wave comes to the end of some kind of a change in the medium, and part of it's reflected and part of it's transmitted. So this happens in strings as well, and this is a little easier to think about because the wave comes in and, well, some of it's going to move the heavy string, but because the heavy string is heavier, it doesn't move it as much, so some of it's reflected. I don't know. Hopefully that's helpful. What's he talking about? I don't know. All right, superposition. So this refers to when two waves overlap. They are superimposed, meaning happen one on top of each other or at the same time. So here we have a pulse coming in like this and a pulse coming in like this, and this is right where they overlap. Let's see, pulses overlap precisely for an instant. So instantaneously, it looks like there's nothing there, but there actually is. There's a wave traveling this way and there's a wave traveling this way, but they just overlap and cancel out. And then afterwards, this wave would be going that way and this wave would be going that way. When the two waves are heading towards one another and they're both upright, we get this type of a situation. You see how the waves are adding together, and so the amplitude has doubled, and then they pass by and pass by. So they actually pass through one another unhindered, unless there's a lot of friction in the system. So we call this constructive interference, meaning they're adding together, and this destructive interference, meaning they are canceling out. Hopefully somebody has some of those cool noise-canceling headphones, which actually send a sound signal that is basically the reciprocal, or the opposite of the sound waves coming in, and it cancels out and you hear nothing. Totally. So here's yet another example of constructive and destructive interference. So let's look. This looks like constructive, this looks like destructive, this looks like nothing. So let's see what these waves look like. So here, do you see how these waves are in phase? And by in phase, meaning they happen at the same time. Crest and a crest, trough and a trough, crest and a crest. They're happening at the same time. And so this axis could be time or position. And this is height, so we see that the amplitudes add together. These are out of phase. So we see how we have a crest at the same time as we have a trough, and we have a crest at the same time as we have a trough. So you can even assign numbers to these. Let's say this is a positive 2, and down here this is a negative 2, and up here positive 2. Negative 2, and so we talk about, well, negative 2 plus positive 2 is 0. That's right. So destructive interference, and then here, so these are out of phase by 90 degrees, pi over 2 radians. Yeah, the trig connection, and we just get a wave that is out of phase by, this would be 45 degrees when they add together. Alright, so we don't have to get too much into that, but this is what happens. Okay, standing waves and strings. So we've done some stuff with slinkies, hopefully, that looks like this, where you set up standing wave patterns. This is the lowest frequency, the next highest frequency, and the next highest frequency. And so we can call this the fundamental frequency, first harmonic. Wait, yeah, okay, fine. And then the first overtone, and the second overtone, and you don't really have to memorize this, but know that when we talk about an overtone or harmonic, we're talking about some multiple or some higher frequency standing waves that is set up in that same pattern. And then knowing or being able to figure out the relationship between the length of the string or slinky or air column, as we'll see, and the wavelength, that's important. So I'll highlight. So one complete wave would be like this. Alright, middle. So middle, bottom, middle, top, middle. And here's one complete wave. And here is one complete wave. So hopefully that helps in seeing how the length, so the length of the slinky or string is a wavelength plus another half, so 3 halves. And the length is one complete wave, and here the length is only 1/2 of a wavelength. Okay. And again, antinode and node, notice how the nodes, and this, whether the hand is a node, that's a little up to debate, but node is the place where it doesn't move, and then antinode is the place where it moves with maximum displacement. So, we move away from waves and strings, and we talk about sound waves in air. And we've talked about how sound waves are air molecules moving back and forth. They are longitudinal waves. So first, let's look at our musician over here. Got some big lips. Alright, so this is a wind instrument, and I think we could call it a flute. And so the flute is going to have these openings, and the person's going to cover some of them up to make different frequency sounds. So, air is blown over this end, and there's an opening, and then let's say there's an opening over here. So what happens is there's basically an air column, and here it's open, and here it's open, but because the wind is moving over it, it creates these vibrations in the air molecules. And the way we represent, let's see, that was not so hot. The way we represent the movement of the air molecules is like this. That looks a little better. Okay, so out at the ends, because it's open, this is where the air molecules are going to be moving the most. So air molecules moving the most, air molecules moving the most. So they're going back and forth, 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 back and forth. And in the middle is where they'd be really compressed. So we have maximum movement, maximum movement, and we can represent that like this. So I know this is confusing. We have this longitudinal sound wave, movement of air molecules being represented by a transverse wave, but this is just how we draw it. Okay, because we could sit here and draw this. I'm wasting precious video time, but it really takes a long time to draw this, where we have it's rarefied and then compressed and then rarefied air molecules, like that. So this and this is a representation of this. This is what's going on. Okay, so we got maximum movement, maximum movement, and this is how we represent a standing airwave that's set up in the air column. And notice how the dimensions, meaning the length of the air column, are going to determine the wavelength of the standing wave, which therefore affects the frequency. We know this, the velocity of sound is equal to the frequency times the, whoa, what? Alright, that's looking better. So velocity is frequency times wavelength. So the speed of sound in air, which we'll talk about soon, is going to be the same for no matter what the shape of the musical instrument is. So the wavelength is going to affect the frequency, and the frequency is what you actually hear. So we have high pitch, that's a high frequency, and we have low frequency, that's a low pitch sound. So, two types of air columns. One we call closed, where one end is open as one end is closed. We'll do some experiments with this. And I think for most wind instruments it ends up being this type of a situation where both ends are open. One end of the instrument is open, and the other end of the instrument is where the musician blows into it and creates the vibrations in the air. So, if one end is closed, I think our standing waves would look like this. So we have closed, meaning no movement. So we have a node. So let's say that this end is closed. You could write closed there. I'm too lazy. And I'm not too lazy. I'm just trying to conserve time. So closed, minimal movement. These would be nodes. These are going to be antinodes because they're open and have maximum movement. That would be a good thing to write for all of those. Alright, so lowest frequency. And next, highest frequency, we have minimum movement, so a node. No, that's not right. It's going to go like this. Right. Like this, and then like this. Okay. So, antinode, maximum movement of air molecules, open end. Node, minimum movement of air molecules, closed end. And we're going to talk about frequencies and wavelengths and all that jibber jabber. When both ends are open, we have this type of situation, which I drew above. So this would be the lowest or fundamental frequency. And then we're going to have a situation that looks like this. So this would be the next highest frequency. Notice how the wavelength is getting shorter. It's getting more compact, meaning the frequency is increasing. And then we would have a situation like this. Okay, so let's talk about the relationship between the length of the air column and the wavelength of the standing wave, and then the frequencies. So this would be the fundamental frequency, so we can just call that F. The length, so obviously this is the length of the air column, and we're thinking about the wavelength, the relationship between the length of the air column and the wavelength of the standing wave. So you might see if you could figure this out. But, so I'll pause for a moment. Alright, got it? Maybe. So the length of the air column is equal to 1/4 of the wavelength. For a second situation, so the next highest frequency that will actually resonate in this air column, we can say that the length of the air column is 3/4 of a wavelength. And for our next highest frequency, the length of the air column will be 5/4 of a wavelength. So we have one complete wave plus another fourth. 1/4, 2/4, 3/4, 4/4 would make a complete wave. And then if we consider the relationship between the length and how that's going to affect the frequency, all right, let's take a look at the wavelength. Notice how this increased by half a wavelength, and how this increased by half a wavelength. So because velocity equals frequency times wavelength, if the speed of sound remains the same, frequency and wavelength are inversely proportional, or reciprocals. So do you see how the wavelength, so we had 1/4 and it goes to 3/4, so that was 1/4 and 3/4. So multiplied by 3. So this is going to be 3 times the frequency, and this would be 5 times the frequency. If we look at the open air column, let me go back to that because I think that was unclear. Longer wavelength dramatic pause there. Longer wavelength means lower frequency. The shorter the wavelength gets, the higher the frequency is. So if we were looking at, this is going to get a little crowded, but who cares? If we're looking at our wavelength, the wavelength is 4 times the length. And if we were looking at our wavelength, the wavelength is 4/3 the length. And here, for a third situation, the wavelength is 4/5 the length. So, see how we divided by 3? So we multiply by 3. And we divided by 5, so we multiplied by 5 when we're talking about the difference between the wavelength and the frequency. So shorter wavelength, higher frequency; longer wavelength, lower frequency. And sometimes you see this with people, actually, like these really tall people, and just because they have these really long vocal cords, they have these deep voices. It's not always the case, but sometimes. Okay, standing air column open at both ends. I'm going to leave this for you. The answers are on the next slide, but I want you to try to. So you're going to call the first, the fundamental, the lowest frequency. And I'd like you to try to write a relationship between the length of the air column and the wavelength of the standing wave that is set up. And then if this is the fundamental frequency, what will the frequency of this be and what will the frequency of this be? Okay, so you do that. And before we go, let's talk about this type of situation. So we're going to do this lab in class where we measure the speed of sound in air using a tuning fork. And this is a graduated cylinder that's almost filled with water. And then we have this empty, like a PVC pipe, and it can move up and down. So you're going to hold, oh, you have short fingers today. You're going to hold the air column, and you can adjust the length. So this end is closed, right, because the sound waves will bounce off the water. And this end is open, and you're gonna bing, hit a tuning fork and set it right above, and we're gonna find the length at which there is some a standing wave setup. So you'll hear resonance, meaning an increase in volume of the sound wave. So let's pretend that you, with your short fingers, are adjusting the air column, and we have a tuning fork up here, and let's say this is a C note. So middle C, 256 hertz, and you adjust and you find that it resonates, meaning creates a louder volume sound when the length of the air column is 34 centimeters. So based on this data, can we calculate the speed of sound in air? Totally. So here's a representation of our lowest, and it'll be the fundamental frequency that actually resonates. You might hear a little bit of the higher ones, but probably not so much. So if this is a situation, we know that the length of the air column, 34 centimeters, so that is 34 centimeters, is related to our wavelength, but our wavelength keeps going, right? So our wavelength in this situation is 4 times the length. Where's our 4? There's our 4. So our wavelength would be 4 times 34 centimeters. We're going to put this in meters, of course. And after multiplying, what do we got? 1.36 meters for a wavelength. And for a sound wave, this is reasonable. And then, let's see, velocity. So the speed of sound in air is equal to the frequency times the wavelength. and we know the frequency of sound. Our tuning fork right here, we'll see 256 hertz. So let's see, 256 and then times 1.36 meters. So this is hertz and this is meters, and our calculator, who knows where it went. So I'm going to get on Desmos on the, oh, it's right here, but it has no batteries. Desmos, and turns out that our speed of sound, as we calculate based on this hypothetical made-up data, is times 348, and that would be in meters per second. This is meters. Whoa, that's hertz, which is like a per second, and this is meters, so we have meters per second. And this is a pretty reasonable value for the speed of sound in the air. We say that at sea level and room temperature, it's 343 meters per second. So this is the value you will see in physics books and stuff. In Mammoth, because air is less dense, we're going to get different values, though. So that's it for now. That was a lot. Oh, that's not it for now. Put it on pause, you poor kids. And what are you doing? You're figuring out these relationships, and then I will move to the next slide and show you the answers. So this was for open at both ends. This is the one you're figuring out. We got the fundamental frequency. What am I looking at? Length, oh, 1/2 wavelength, okay, and then length is equal to wavelength, and then length is equal to 3/2 the wavelength. Let's see, so we have down, oh yeah, 1.5, okay, so bottom to bottom and then to top, so 1.5. And then where's our relationship with the frequencies? It is this, here's our fundamental, and then this would be twice, and this would be 3 times, which is different from what we had with the one end that was closed. We had frequency, 3 times the frequency, and 5 times the frequency. So if you got this and this and this for the relationship between the length and the wavelength, cool. And if you got this, fundamental frequency, twice the fundamental frequency, and 3 times the fundamental frequency, then great work. Let's take a look. This is what we already went through. All these images are from your book, by the way, which is an excellent book. We got relationship between length and wavelength. And we have the fundamental frequency, and then 3 times the fundamental and 5 times the fundamental frequency. So that was a lot. I know, I apologize, but it turns out that YouTube accepts videos longer than 15 minutes, so I get to just ramble on and on.